Hi, everybody. Welcome to another Chats with Chaudhry. I hope you're safe and well. Today, I'm joined by Chris Adams, who is the Bruker Daltonics Global Business and Product Manager for Integrated Proteomics. So you can guess, yes, we're going to be talking about proteomics today. So, hi, Chris. How are you?
I'm very good. Thank you. Thank you, Rizwan.
Well, it's lovely to meet you.
How are you?
I'm very well, actually. Thank you very much. And I understand you've been promoted, so congratulations on your new role.
Well, thank you. Yes, it's an exciting new opportunity, and I think there's a really bright future ahead. So yes, thank you. I appreciate that.
Well, it's a pleasure. And so before we start talking about proteomics itself, perhaps you can tell those people who are not familiar with Bruker Daltonics a little bit about the business and also your role within that.
Okay, so Bruker Daltonics is the mass spectrometry division of Bruker Corporation. So Bruker makes analytical instrumentation, as you well know. And then within the mass spectrometry group, my focus is on proteomics, which is the qualitative and quantitative study of proteomes, right? Fantastic. And then my new role specifically within that is to integrate our hardware, like the Timstoff Pro, for example, with the data analysis and other software packages to make the user experience more seamless, and then also, most importantly, I think there's an opportunity to make our experiments more informative as well.
Fantastic. Okay, so that's brilliant. So start to finish, what does the proteomic process look like?
Well, that could be a very long answer. So let's keep it brief. So, well, it starts with a sample of interest, and that could be anything from a virus particle to blood or tissue, or the combination of all three of those. And then the important part there is to extract the proteins from that sample type. And then we take traditionally we take those proteins and then we digest them to smaller pieces called peptides.
Right.
And then we introduce those peptides to the mass spectrometer, where they're ionized. This is commonly done with high performance liquid chromatography, which I'm sure you're very familiar with.
Sure.
We do that to basically, make what is hundreds of thousands, if not millions, of these little peptides more manageable when we look at them in an additional dimension. And then the mass spectrometer can select from many of those hundreds or thousands of things and sequencing them at a very fast speed, right? So that sequencing is called MSMS or fragment ion step, and from that we get the primary amino acid sequence of that particular peptide. But then at the end, all of this data that we generate has to be analyzed, and it will inform us as to what is present within the sample. And we've been doing this now for many years with software and other sophisticated database search algorithms. But that's just as I said, that's just that informs you what's there. So that's the qualitative nature, but that's not quantitative. So additionally, what you really want to know is not just what's there, but how much of it.
Right.
And so to do the quantitation, we again return to our friends that are software tools, and we can ask questions like, within all of these samples that we've analyzed, can we correlate particular proteins and their expression as a function of some disease state or drug treatment, et cetera. So, start to finish, I would say that's the brief of what proteomics looks like.
Well, thank you for that, because I'm a non-scientist, so that actually explains something I didn't know before. So thank you for that. So when Bruker launched the Timstoff Pro, has that, by launching that, has that had an impact in any of those steps in terms of the process for scientists?
Right. Yeah. In fact, there's been a number of attributes that are part of the Timstoff Pro that have led to some real advantages for proteomics researchers. So I mentioned that the instrument needs to be able to look at many hundreds of thousands of things in a short amount of time. So it needs this speed. the sequencing speed of the instrument, which is very critical. So the Timstoff Pro, the way that it's designed, can perform these sequencing events incredibly fast, about 3 to 5 times faster than the nearest competitor. And it does this simultaneously boosting its sensitivity. So that's a huge advantage when you are presented with really complex mixtures, that you can get through more of those things that are there in a short amount of time. Right. The second point that's really actually quite important as well that I would mention is that the trapped ion mobility function of the Timstoff Pro allows you to move the ions not only by their what's known as their mass to charge ratio, but also by their collisional cross section. So that's an additional dimension that we get from the data, and all the other instruments rely specifically on the mass to charge to select an ion of interest. So what that means really experimentally is that any ions that are nearby to the ion of interest, that particular mass to charge of interest, if you're selecting for that particular ion, and you will, because this always happens in these proteomics experiments, that you will inadvertently pick an adjacent MZ value, mass to charge ion. And the result there is called a chimeric spectra, because both of those guys are incidentally fragmenting at the same time. Right. And those are, those are dirty spectra, for lack of better description, and those are more challenging for the database search algorithms to assign and pick out. So that's where that inherent advantage of the additional dimension that is collisional cross section gives you a lot of value. Right. And then, if I had to mention one other thing that's a differential, is now that this new dimension exists, the collisional cross section becomes an inherent property of the peptide. So that's to say that when you measure that value, yeah, it's exactly the same in your lab as it is in my lab, as it is in all those other labs around the world. And we can utilize that in these data analysis steps in the software packages that I've been describing. So yeah, there are some key advantages that the new technology has delivered for proteomics researchers.
Well, this is interesting. And I know you already alluded to this in the opening introduction. We talked about you've got a new role. So your new role focuses on data analysis. How did that originate?
Yeah. So funny story. So, well, I guess it's not funny, but it's been a fantastic ride. So it actually originated with a collaboration. So we, there's a group led by a key opinion leader at the Scripps Institute in San Diego, and his name is Professor John Yates, and his group had been experimenting.
At SMS, actually, yes.
Yeah, right. He's been a field leader for many years. So great. I'm glad that you saw that, and it's been really tremendous to work with his group. So actually, I was there with some of our software team, and we were having discussions with his team. And we realized that they had a GPU-based search algorithm that had been developed by Robin Park, and who would form a spin-off company founded out of this lab. So we had some additional discussions, and we decided to take next steps, which were including hosting them at our site in Bremen. So to see if this is a reality. And what came out of that was the ability to search these spectra instantaneously, or basically in real time. So that this GPU-based search algorithm was so fast that ions would arrive from the detector on the acquisition PC of the mass spectrometer. We could move those through this search algorithm and assign the peptide sequence in real time kind of processes. So, we saw just an immense opportunity here, a lot of value, because, as I've already described, we can go, the mass spectrometer can scan really fast, and you get this additional information content or data-rich files, where the end result is many more files that are even more rich in content. So instead of a lab that was formerly, generating, let's say, 10, 12, 15, 20 runs a day, now we can easily generate, 50, 100, up to 300 LC-MS proteomics runs in a single day. So now what's happened is that we've shifted the bottleneck. We can go faster, so we're generating more data, and now our biggest problem becomes this data processing step. So that's immediately where we saw how a real-time search capability could address this problem.
Right. So now that through this collaboration with the Yates Lab, you've made this real-time search a reality on the Timstoff Pro, what's the next steps, or what's it look like going forward?
Right. So that's why I'm so excited about this new role and the opportunities, because we have just a bunch of different ideas, directions where to take this. So in its first iteration here at HUPO 2020, coming up in just a week or so,
right,
we will actually launch this real-time search capability for all current and new Timstoff Pro customers.
Right.
And it's called PACER, which is an acronym for Parallel Database Search Engine in Real Time, and it was coined by the Yates Lab in working with them. So, as I said, it's a GPU-powered workstation. It sits adjacent to the acquisition PC, and as the acquisition PC relays the MS info,
yep.
It does the sequencing and stores that real-time data on the PACER box. And now, since we can perform thousands of processes simultaneously, that's the beauty of GPU. Then we get these results so fast. So effectively, the ions come in and peptide sequences come out. Or another way to think of that is what we're saying, run and done. So
I've heard that. I heard it in your presentation at SMS. I remember.
Good. Yeah, I hope. I think that means a lot to a lot of different labs. Right.
Good.
So hopefully, the idea here is where we formerly had this bottleneck. That is data analysis. Hopefully, we can break that and push through there.
All right. So, in addition to knowing the results, as soon as you've got the acquisition, is complete, what are some of the other advantages of real-time search?
So, real-time, real-time's actually been out there for a number of years. So we're not the ones to envision this from conception or even experimentally. But our approach has a number of advantages. First, as I've mentioned and kind of stressed here, that it is GPU based, so it's blazingly fast, right? Which is different than previous approaches. And then also we're leveraging the real-time search results that you get from the PACER box or run and done to inform how your sample acquisition queue should proceed. And this is really important. So the way this is going to work is that we will ask the user to input a predetermined metric, a qualifying metric. So that could be, in the case of a QC sample, the number of proteins or peptide identifications that you expect from this particular sample. Or you could imagine for people doing work where LFQ or quantitation is super important, it could be a blank sample, and you would want basically nothing in there. And then you enter that qualifier, and you can be sure that that qualifier is defined after the run and done process is complete, and those real-time search results will be queried against that qualifier. If the qualification or specification is met, then the sequence queue can progress. And then if it's not, then the acquisition queue will halt.
Right. So why would you want to stop the acquisition queue?
Right. So you would want to stop the acquisition queue for a number of reasons. Precious samples, right? Just think about that. We have a lot of collaborators running COVID samples right now, and you can definitely imagine how unfortunate it would be if you lost a series of those precious samples because the instrument was out of specification and you didn't know until it was too late. Aside from the samples being precious, they also can be extremely expensive. So when you're using some of these labeling technologies, stable isotope labels, or other isobaric tags, you're dealing with enrichment. So there's a lot of our users do phospholipeptide enrichments or acetylation enrichments, et cetera, looking for all these different PTMs. Those kits to study those samples are extremely costly. So you can save a ton of money in reagents and operator time that it takes to prepare those samples. And actually, Rizwan, it's funny, before I joined Bruker here about 3 years ago, I used to run the Stanford Proteomics core facility. And there, I can tell you there is nothing worse than arriving on a Monday morning to see that something had gone wrong with your acquisition queue that was supposed to have been running over the weekend, samples just continuously injecting, and then you contact that postdoc, grad student, PI that you've been working with, the time, the effort, the money, the brain power that they've spent to generate these samples, and now with the thought is with PACER 1.0 and run and done, we can add so much more peace of mind to those researchers, and that's just like I used to be.
Yeah, well, as you said, and a lot of those samples may be very unique, and you may not have a lot of those to actually select from in the first place, will you? So you're right, it's very, very important, particularly in the current climate as well, when people are searching for solutions for various illnesses and obviously COVID. Well, that's really, really interesting. If people want to know more about PACER, run and done, and the things that you're doing at the moment, where can they get more information?
So you can go to Bruker.com. You can go to our website. Also, we are having a lot of speakers at HUPO. So, there's a lot of different ways to find our HUPO contacts. We also have a YouTube video on PACER 1.0. And if you go to our webpage at Bruker, you can also find out more information about that as well.
Fantastic. Well, look, don't worry, people. All the links for everything that's just been said will be above this video. So you don't have to write anything down to try and Google for anything. I will put the links above the video so you can hopefully go and visit them at HUPO. Go and have a look at the video and also have a look at some additional information as well on the Bruker website as well. So, Chris, all that I can say is congratulations once again on the promotion. Obviously, your stuff. It's very, very interesting as well. So thank you very much for that. I hope everybody else found that useful as well. If you want more information, say check out the links and check out the HUPO booth at Bruker booth at HUPO, if I get it the right way around. So all that stuff says, Chris, thank you very much for your time.
Thank you, Rizwan. It was a pleasure.
Yeah, and for those who don't know, actually, Chris has got his curtains drawn at the moment, but it's sort of morning in California, where it's San Jose, and the sun's starting to break out. It just looks like it's at night time. Whereas I'm in the UK at the moment, and it's starting to get dark where I am, actually. So there you go. So I hope you'll find that useful. As always, until next time, stay well and stay safe. Thanks a lot. Bye-bye.